every type of rocket engine. Space is complicated. We make it simple. Every rocket engine ever built solves the exact same problem in the exact same fundamental way. Throw mass out the back as fast as possible, and the rocket gets pushed forward. That's it. That's the entire principle behind every launch, every satellite, and every spacecraft that has ever left Earth. What actually changes category to category is what gets thrown, how it's thrown, and how efficiently the whole process converts stored energy into usable thrust. We're going in order from the earliest, simplest engines to the most exotic, least flown ones. Then we'll sort them a second way by the specific trade off each one makes between raw power and efficiency. Because on this list, no engine gets to have both. Solid rocket motors. We begin with the oldest, simplest design on this entire list, one that predates modern rocketry by centuries. A solid rocket motor is, at its core, a sealed tube packed with a solid propellant mixture that, once ignited, burns continuously and violently until it's completely consumed, producing thrust the entire time with no moving parts and no way to shut it off partway through. Here's the fact that should genuinely bother you. Once lit, a solid rocket motor cannot be throttled, paused, or safely extinguished. The same simplicity that makes it cheap, reliable, and capable of sitting in storage for years without maintenance also means there is no abort option once ignition begins. A real design constraint engineers have to build entire mission profiles around. The Space Shuttle's twin solid rocket boosters, among the most powerful solid motors ever flown, provided the overwhelming majority of the vehicle's total thrust at liftoff, precisely because solid motors excel at generating enormous immediate power exactly when a rocket needs to fight its way off the launch pad against Earth's full gravity. Here's the part that lingers. This same all or nothing burn profile was directly implicated in the 1986 Challenger disaster discussed elsewhere on this channel, where a failure inside a solid rocket booster seal could not be paused, contained, or corrected once ignition had already begun. Liquid-fueled rocket engines. Here's the twist. Unlike a solid motor's one continuous uncontrollable burn, a liquid engine separates its fuel and oxidizer into two separate tanks, pumping them together into a combustion chamber only when needed, meaning the engine can be throttled, shut down, and in some cases even restarted mid-flight, a level of control a solid motor simply cannot offer. Here's the fact that should genuinely bother you about how difficult this actually is. Precisely controlling the combustion of two separate, often cryogenically frozen liquids pumped together at extraordinarily high pressure and ignited in a chamber reaching thousands of degrees remains one of the most demanding engineering problems in all of aerospace, and even decades into the space age. A meaningful fraction of new liquid engine designs still fail during early testing. The Saturn V's -1 engines, still among the most powerful single rocket engines ever flown, burned refined kerosene against liquid oxygen to lift Apollo missions off the launch pad, while many modern engines instead burn liquid hydrogen for its superior efficiency once a rocket is already moving. Here's the part that lingers. This exact category, controllable, restartable, and precisely throttleable, is what makes complex maneuvers like an orbital rendezvous or a soft lunar landing possible at all. A solid motor could get you off the ground, but only a liquid engine can gently set you down somewhere else. Hybrid rocket engines. Here's the reframe. What if you could combine a solid motor's simplicity with a liquid engine's controllability? A hybrid rocket engine uses a solid fuel grain, similar in concept to a solid motor's propellant, combined with a separate liquid or gaseous oxidizer that's pumped in and can be throttled or shut off on command, splitting the difference between the two previous categories. Here's the fact that should genuinely bother you. Hybrid engines are generally considered significantly safer to handle and store than either pure solid or pure liquid engines because the solid fuel component alone, without its oxidizer, is typically inert and won't ignite or explode accidentally, while the liquid oxidizer can be safely stored separately until the moment of use. Here's the part that lingers. Despite these safety advantages, hybrid engines have historically underperformed both solid and liquid designs in terms of raw thrust efficiency and have mostly been used in suborbital and experimental vehicles. including Spaceship One, the first privately funded crewed spacecraft to reach space, rather than in the large orbital rockets that dominate the rest of this list. A genuinely promising middle ground that has, so far, mostly stayed in the middle of the industry, too. Staged combustion engines. Here's the fact that pushes liquid engine design to its most efficient extreme. A staged combustion engine burns a small portion of its propellant first in a separate preburner, using the resulting hot gas to drive the turbopumps before feeding that already burned gas back into the main combustion chamber to be burned again alongside the rest of the propellant, extracting significantly more usable energy from the same fuel than a simpler engine design would. Here's the fact that should genuinely bother you about how demanding this design actually is. Routing already combusted, still burning gas back into a second combustion stage requires extraordinarily precise engineering to prevent catastrophic overheating or instability, which is exactly why staged combustion engines remained almost exclusively a Soviet and Russian specialty for decades, most notably in the RD 180 engine, before other countries fully mastered the technique. Here's the part that lingers. This specific design choice is a major reason certain modern reusable rockets can achieve the efficiency needed to launch, land, and refly the same engine hardware repeatedly, extracting enough performance from every drop of propellant to make reusability an economically viable strategy rather than just an engineering curiosity. Ion and electric propulsion engines. Here's the fact that reframes this category as running on an entirely different scale of physics. Unlike every chemical engine described so far, which generates thrust through violent rapid combustion, an ion engine generates thrust by electrically accelerating charged particles, usually xenon gas, out the back of the spacecraft at extremely high velocity, producing only a tiny, gentle amount of instantaneous thrust, often no stronger than the weight of a single sheet of paper. Here's the fact that should genuinely bother you. Because that tiny thrust can be sustained continuously for months or years rather than burning out in minutes. An ion powered spacecraft can eventually reach far higher total velocities than any chemical engine ever could, simply through patient, uninterrupted acceleration. The same fundamental trait discussed elsewhere on this channel regarding interstellar propulsion concepts. Here's the part that lingers. No ion engine could ever lift a rocket off Earth's surface against the planet's own gravity, meaning this entire category only becomes useful once a spacecraft is already in space, making it exclusively a deep space and orbit adjustment technology rather than a launch technology at all, the opposite trade off from the solid motors that open this list. Nuclear thermal rocket engines. Here's the fact that closes the gap between chemical power and something genuinely more extreme. A nuclear thermal engine uses a compact onboard nuclear reactor to directly superheat a propellant, typically liquid hydrogen, before expelling it out a conventional rocket nozzle, achieving significantly higher efficiency than any chemical engine because the reactor can heat the propellant to extreme temperatures without needing to also burn it as fuel. Here's the fact that should genuinely bother you. This isn't purely theoretical. Both American and Soviet space programs ground tested working nuclear thermal engines decades ago, achieving real measured performance improvements over comparable chemical engines before both programs were ultimately shelved rather than flown, largely for political, safety, and funding reasons rather than any confirmed engineering failure. Here's the part that lingers. Nuclear thermal propulsion has recently seen renewed serious interest for potential crewed Mars missions, specifically because its efficiency advantage could meaningfully shorten transit time, directly reducing a crew's total radiation exposure during the multi month journey discussed elsewhere on this channel, meaning a propulsion technology first tested in the 1960s may end up being the specific engine that finally gets used decades after ground testing first proved it worked. Aerospike and altitude-compensating engines. Here's the fact that closes this list with an engine designed to solve a problem most people never realize exists. A conventional rocket nozzle is physically shaped for peak efficiency at one specific altitude and atmospheric pressure, meaning it's actually somewhat inefficient during both the earliest low altitude portion of a launch and the later near vacuum portion, only briefly passing through its truly optimal operating point in between. An Aerospike engine flips the entire nozzle design inside out, using the surrounding atmosphere itself as part of the effective nozzle shape, automatically adjusting and compensating for changing air pressure throughout the entire ascent, remaining closer to peak efficiency across the full range of altitudes a rocket actually flies through. Here's the fact that should genuinely bother you. Despite decades of research and several serious development programs, no Aerospike engine has ever successfully flown on an operational orbital rocket, repeatedly canceled due to a combination of cooling challenges, manufacturing complexity, and funding cuts, even though the underlying physics has been demonstrated and understood since the 1960s. Here's the part that lingers. Aerospike engines remain one of the most persistent, almost there technologies in the entire history of rocketry, theoretically superior across an entire flight profile, and yet decades later, still waiting for the specific combination of funding and engineering follow through needed to actually put one into orbit. Ramjets, scramjets, and air breathing engines. Here's the fact that closes out the engine categories with the one design that deliberately avoids carrying its own oxidizer at all, at least for part of the journey. A ramjet or scramjet engine draws in surrounding atmospheric oxygen directly, compressing incoming air using nothing but the vehicle's own forward speed rather than a mechanical compressor, and burning it against onboard fuel, meaning the vehicle only needs to carry fuel, not the heavier oxidizer every rocket engine described so far has to haul along as dead weight for the entire flight. Here's the fact that should genuinely bother you. This only works within an atmosphere and only above a minimum forward speed needed to compress incoming air enough for combustion, meaning no air breathing engine on this list can function in the vacuum of space at all, or get a vehicle moving from a complete standstill on the ground. Here's the part that lingers. Several proposed next generation launch concepts envision a hybrid vehicle that starts on air breathing engines to save weight during the earliest, densest part of the atmosphere, then automatically transitions to a conventional rocket engine once the air becomes too thin to use. A genuinely promising idea that, like the Aerospike engine described elsewhere on this list, has proven far easier to design on paper than to actually certify and fly. Let's sort these 8 again a different way, not by how they work, but by the specific trade off each one makes between raw power and efficiency. On the maximum power end, solid rocket motors, delivering immediate, overwhelming thrust with no ability to throttle or control the burn once started. On the balanced and controllable end, liquid fueled and staged combustion engines, sacrificing some of a solid motor's raw simplicity in exchange for precise control and dramatically higher efficiency. On the safety optimized middle ground, hybrid engines trading peak performance for a level of built in safety neither pure solid nor pure liquid designs can match. On the patient and efficient end, ion propulsion, incapable of launching anything off a planet, but ultimately capable of reaching higher total speeds than any chemical engine given enough uninterrupted time. On the highest potential efficiency end, nuclear thermal engines proven decades ago but never yet flown operationally. And on the theoretically superior but unflown end, Aerospike engines, a genuinely better idea on paper that has, so far, never made it past the paper stage into an actual orbital launch. It's worth understanding before we close how engineers actually compare wildly different engine types against each other in the first place, because power alone doesn't tell the whole story. The standard metric is called specific impulse, essentially a measure of how efficiently an engine converts propellant into usable thrust over time. A solid motor might deliver enormous instantaneous force, but relatively low specific impulse, while an ion engine delivers barely any instantaneous force at all, but an extraordinarily high specific impulse sustained over months. Here's the fact that should genuinely bother you. No single engine on this entire list scores well on every metric simultaneously, meaning every real spacecraft mission involves a deliberate trade off, often combining multiple engine types from this list on the same vehicle, using one category to escape a planet's gravity and a completely different category once safely in space, rather than any one engine ever being the universally correct choice. Here's the last thing worth sitting with. Every single engine on this list is solving the exact same one-line physics problem that's been true since the first rocket ever left the ground. Throw something backward hard enough, and you get pushed forward. Everything else, every category, every trade-off, every decades-long engineering argument between power and efficiency is just humanity arguing over the best possible way to do that one simple thing. Not bad for stick figures on a rock,